In the vast expanse of the cosmos, amidst the swirling galaxies and shimmering nebulae, lurk objects of immense power and mystery, black holes. These celestial entities, once relegated to the realm of science fiction, have captivated the imaginations of scientists and stargazers alike for centuries. Their gravitational pull is so strong that nothing, not even light, can escape their grasp, rendering them invisible to the naked eye. Yet, despite their elusive nature, black holes have emerged as some of the most studied and awe-inspiring objects in the universe. Black holes challenge our fundamental understanding of physics, pushing the boundaries of space, time, and gravity. They are born from the death throes of massive stars, collapsing under their own weight to form infinitely dense points known as singularities. These singularities are shrouded by event horizons, points of no return beyond which the fabric of spacetime is irrevocably warped. The study of black holes has revolutionized our understanding of the cosmos. They are no longer seen as mere cosmic oddities but as integral components of galactic evolution, influencing the birth of stars, the dynamics of galaxies, and the very structure of the universe itself. Their existence has forced us to confront the limitations of our current knowledge and to seek new explanations for the workings of the cosmos. The concept of black holes has been pondered by scientists and philosophers for centuries. As early as the 18th century, John Michell, an English natural philosopher, proposed the existence of dark stars, massive objects whose gravity could trap light. Similarly, French mathematician Pierre-Simon Laplace independently formulated the idea of celestial bodies so dense that their escape velocity would exceed the speed of light. However, century, with the advent of Albert Einstein's theory of general relativity, that the true nature of black holes began to be understood. Einstein's groundbreaking theory revolutionized our understanding of gravity, describing it not as a force, but as a curvature of spacetime caused by the presence of mass and energy. Einstein's equations predicted the existence of objects so massive and compact that they would warp spacetime, creating regions from which nothing could escape. These objects, initially met with skepticism, would later become known as black holes. In this documentary, we embark on a captivating journey into the heart of darkness, exploring the history, science, and mysteries surrounding black holes. From the early speculations of dark stars to the groundbreaking discoveries of gravitational waves and the first-ever images of these enigmatic objects, we delve into the captivating story of black holes. Our exploration will take us to the edge of the observable universe, where we will witness the awe-inspiring power of black holes as they shape galaxies and warp the fabric of spacetime. We will journey to the event horizon, the point of no return, and peer into the abyss, seeking answers to some of the most fundamental questions about the nature of gravity, the fate of information, and the ultimate destiny of the universe itself. Join us as we unravel the secrets of these cosmic enigmas, venturing into the shadows of infinity to uncover the profound implications that black holes hold for our understanding of the cosmos and our place within it.
Imagine a time before the roar of rockets, before the glow of electric lights, a time when the universe was understood through the lens of telescopes pointed toward the heavens and the elegant equations scribbled in dimly lit studies. It was in this era, the late 18th century, that the seeds of a radical idea were sown, a concept so bizarre and audacious that it would take centuries for science to catch up and confirm its reality. This was the genesis of the black hole. An object so dense, so gravitationally powerful, that it could trap light itself. The very notion of a dark star, a celestial object that could devour light, seemed more at home in the pages of a Gothic novel than in the annals of scientific inquiry. Yet two brilliant minds, separated by miles and circumstance, would independently stumble upon this perplexing possibility. Their names were John Michell and Pierre-Simon Laplace, and their ideas, though nascent and incomplete, would lay the groundwork for one of the most profound revolutions in our understanding of the universe. Their journey into the darkness began not with telescopes or observatories, but with a simple yet profound question: what is the nature of gravity? At the time, Sir Isaac Newton's law of universal gravitation reigned supreme. explaining the motions of planets and the dance of celestial objects with elegant precision. But Newton's theory, though powerful, lacked a crucial element: an understanding of light's relationship to gravity. This gap in understanding would set the stage for Michell and Laplace's revolutionary insights. John Michell, an English natural philosopher, astronomer and clergyman, possessed a mind that roamed freely across the cosmos. He was a true polymath, his interests spanning fields as diverse as geology, seismology, and even the design of scientific instruments. Yet it was his fascination with the heavens that would lead him to contemplate the unthinkable. In 1783, while pondering the implications of Newton's law of gravity, Michell conceived of a star so massive, so gravitationally potent, that its escape velocity would exceed the speed of light itself. Escape velocity, in essence, is the speed an object needs to achieve to break free from the gravitational pull of another, more massive object. For Earth, escape velocity is a brisk 7 miles per second. For the Sun, much more massive, it's a scorching 383 miles per second. But for Michell's hypothetical dark star, the escape velocity would surpass the cosmic speed limit: 186,000 miles per second, the speed of light. This meant that nothing, not even light, could escape the clutches of such a monstrous object. Michell reasoned that these dark stars, though invisible to the eye, could still exert a gravitational pull on nearby stars, betraying their presence through the subtle dance of celestial objects. Michell's idea, though groundbreaking, was purely theoretical. He lacked the mathematical tools and the observational evidence to fully develop his concept of dark stars. However, his work planted the seed of an idea that would continue to germinate in the minds of scientists for generations to come. Across the English Channel, a French mathematician named Pierre-Simon Laplace was independently arriving at a similar startling conclusion. Laplace, renowned for his work on celestial mechanics and probability, was deeply engrossed in the study of gravity and its implications for the cosmos. In 1796, Laplace published his seminal work, Exposition du système du monde, in which he explored the possibility of corps obscurs or dark bodies existing within the universe. Like Michell, Laplace reasoned that sufficiently massive stars could possess gravitational fields so intense that light itself would be unable to escape. Laplace, however, went a step further than Michell, employing his formidable mathematical prowess to calculate the size such a dark body would need to possess in order to trap light. He concluded that a star with the same density as the Sun, but with a diameter 250 times greater, would be invisible to distant observers. Despite their independent discoveries, both Michell and Laplace's ideas about dark stars were met with a mixture of intrigue and skepticism. The prevailing scientific understanding of light at the time was rooted in Newton's corpuscular theory, which depicted light as a stream of particles. The idea that these particles could be influenced by gravity, let alone trapped by it, seemed inconceivable to many. The scientific community, steeped in Newtonian physics and lacking the observational tools to detect such faint objects, largely relegated the concept of dark stars to the realm of mathematical curiosities. Michell and Laplace's ideas, though brilliant in their foresight, were simply ahead of their time. The 19th century witnessed a revolution in our understanding of light with the advent of James Clerk Maxwell's theory of electromagnetism. Maxwell's equations, published in 1865, elegantly unified electricity, magnetism, and light, demonstrating that light itself was an electromagnetic wave. This discovery further complicated the already perplexing question of light's interaction with gravity. The Newtonian framework, which had served as the bedrock of physics for centuries, was beginning to show its limitations. It could not adequately explain the behavior of light in the presence of strong gravitational fields, nor could it account for the strange anomalies that astronomers were beginning to observe in the motions of stars and galaxies. The universe, it seemed, held secrets that lay beyond the grasp of classical physics. A new theory, one that could reconcile gravity with the nature of light and space-time, was desperately needed. The stage was set for a revolution, one that would reshape our understanding of the cosmos and bring the whispers of dark stars back from the shadows. Despite the prevailing skepticism surrounding the existence of dark stars, their echoes persisted in the scientific literature. Astronomers, armed with increasingly powerful telescopes, began to observe phenomena in the cosmos that hinted at the presence of incredibly dense, compact objects lurking in the depths of space. Binary star systems, where two stars are locked in a gravitational dance around a common center of mass, provided tantalizing clues. In some of these systems, astronomers noticed that one star would exhibit unusual orbital behavior, as if being tugged upon by an unseen companion. These unseen companions, some theorized, could be the elusive dark stars predicted by Michell and Laplace. Furthermore, the discovery of X-rays in the late 19th century and the subsequent development of X-ray astronomy in the mid-20th century opened up new windows into the universe. Astronomers detected powerful X-ray sources emanating from certain regions of space, suggesting the presence of extremely hot and dense objects that defied explanation by conventional stellar models. These observations, though indirect, provided compelling evidence for the existence of objects far more compact and gravitationally powerful than any previously known. The whispers of dark stars, once dismissed as mere theoretical curiosities, were beginning to grow louder, demanding the attention of the scientific community. The dawn of the 20th century brought with it a seismic shift in our understanding of the universe. In 1905, a young Albert Einstein, working as a patent clerk in Bern, Switzerland, published his groundbreaking theory of special relativity. This revolutionary theory, with its elegant equation energy equals mass times the speed of light squared, shattered the Newtonian view of a static absolute universe, replacing it with a dynamic relative one where space and time were intertwined. But Einstein's revolution was far from over. He spent the next decade grappling with a far more challenging task, incorporating gravity into his relativistic framework. In 1915, after years of intense intellectual struggle, Einstein presented his masterpiece to the world, the theory of general relativity. General relativity, a triumph of human ingenuity, redefined gravity not as a force acting at a distance, but as a curvature of space-time caused by the presence of mass and energy. Einstein's equations, elegant in their simplicity yet profound in their implications, provided a new lens through which to view the cosmos, one that would ultimately illuminate the true nature of Michell and Laplace's dark stars. With the advent of general relativity, the stage was set for a new era of astrophysical exploration. The whispers of dark stars, once lost in the void of scientific uncertainty, were about to become a roar, heralding a revolution in our understanding of the most extreme objects in the universe.
Across the vast expanse of the cosmos, stars are born. They blaze with fiery brilliance, and ultimately, they meet their demise. While smaller stars, like our own sun, fade into white dwarfs at the end of their lives, massive stars, those many times heavier than our sun, are destined for a far more dramatic and violent fate. These stellar giants, fueled by the nuclear fusion in their cores, burn through their fuel reserves at a prodigious rate, their lives measured in millions, not billions of years. And when their internal furnaces finally sputter and die, these behemoths of the cosmos collapse under their own immense gravity, leaving behind remnants of unimaginable density and gravitational pull black holes. Imagine a star perhaps 30 times the mass of our sun, nearing the end of its stellar life. For millions of years it has shone brightly, a beacon in the cosmic darkness, its immense gravity holding sway over a retinue of planets and smaller stars. But the star's internal reserves of hydrogen, the fuel that sustains its nuclear fusion, are dwindling. The outward pressure generated by fusion, which once counterbalanced the inward pull of gravity, begins to falter. The star's core, once a furnace of unimaginable power, contracts under its own weight, its temperature and density soaring to incomprehensible levels. As the core collapses, the star's outer layers are no longer held in check. They come crashing down towards the center with unimaginable force, only to be met by the incredibly dense, compact core. The result is a cataclysmic rebound, a shockwave of unimaginable power that rips through the star, blasting its outer layers into space in a dazzling supernova explosion. For a brief, shining moment, the supernova outshines entire galaxies, a cosmic spectacle visible across billions of light-years. The fate of the stellar core, however, is far more enigmatic. If the core's remaining mass, the heart of the once mighty star, is sufficiently great, typically more than 3 times the mass of our Sun, then no known force in the universe can halt its inexorable collapse. Gravity, now the undisputed master of the star's destiny, crushes the core with unrelenting force. Electrons are forced into protons, forming neutrons, and even these particles, once thought to be the fundamental building blocks of matter, are squeezed together until the core implodes into an infinitesimally small point, a singularity. The singularity, a point of infinite density and zero volume, lies at the heart of a black hole, a region of spacetime where gravity reigns supreme, warping the very fabric of the cosmos. Surrounding the singularity is an invisible boundary known as the event horizon, a point of no return for anything that dares to venture too close. Once an object crosses the event horizon, its fate is sealed. Not even light, the fastest entity in the universe, can escape the black hole's gravitational clutches. This process of stellar collapse, from the death throes of a massive star to the formation of a black hole, is one of the most extreme and violent events in the universe. It is a testament to the power of gravity, the ultimate sculptor of the cosmos, to transform matter and energy into objects of unimaginable density and gravitational pull. Black holes born from the ashes of stellar giants are not merely cosmic curiosities, they are dynamic entities, their immense gravity influencing the evolution of galaxies and the very structure of the universe. In many ways, black holes are cosmic cauldrons, regions of intense activity where matter and energy are churned and transformed. As matter falls towards a black hole, it forms an accretion disk, a swirling disk of gas and dust heated to millions of degrees. This superheated material emits intense radiation, primarily in the X-ray portion of the electromagnetic spectrum. Furthermore, black holes can drive powerful jets of particles that travel at nearly the speed of light. These jets can interact with surrounding gas clouds, triggering star formation and influencing the evolution of entire galaxies. The discovery of black holes was a gradual unveiling, a series of observations and deductions. One of the earliest pieces of evidence for black holes came from the study of binary star systems. In the constellation, Cygnus lies a binary star system known as Cygnus X1. This system, located about 6,000 light-years from Earth, consists of a blue supergiant star and an unseen companion. The blue supergiant is being actively stripped of its outer layers by its companion, forming a swirling accretion disk. However, the unseen companion, dubbed Cygnus X1, emits intense X-rays, far too energetic to be produced by any known type of star. Cygnus X1's mass, estimated to be about 15 times that of our Sun, is far too great to be a neutron star. The only plausible explanation was that Cygnus X1 was a black hole, its immense gravity stripping material from its companion star. This discovery, announced in 1972, provided the first strong observational evidence for the existence of black holes. Galactic architects. While stellar mass black holes are born from the death throes of individual stars, supermassive black holes are entities of a far grander scale. These cosmic behemoths, with masses ranging from millions to billions of times that of our Sun, play a pivotal role in the formation and evolution of galaxies. The presence of supermassive black holes was first hinted at by observations of active galactic nuclei, incredibly luminous objects at the centers of some galaxies. AGN emit vast amounts of energy across the electromagnetic spectrum, often outshining the combined light of all the stars in their host galaxies. The only known mechanism capable of powering such energetic objects is the accretion of matter onto supermassive black holes. As gas and dust spiral inward towards the event horizon of a supermassive black hole, they release gravitational potential energy, heating up to millions of degrees and emitting intense radiation. Supermassive giants enigma at the heart of galaxies. The existence of supermassive black holes raises intriguing questions about the early universe. These colossal objects, with masses equivalent to billions of suns, appear to have formed relatively early in cosmic history. How these behemoths grew so massive in such a short time frame remains one of the most perplexing mysteries in astrophysics. One theory suggests that supermassive black holes formed from the collapse of massive gas clouds in the early universe. These clouds could have collapsed directly into black holes, bypassing the star formation process altogether. Another possibility is that supermassive black holes formed through hierarchical mergers, starting with smaller black holes that gradually merged over billions of years. This process, driven by the gravitational interactions of galaxies, could explain the observed correlation between the masses of supermassive black holes and the masses of their host galaxies. The hunger of giants. Regardless of their origins, supermassive black holes continue to exert a profound influence on the galaxies they inhabit. Their immense gravity shapes the distribution of stars and gas, regulating star formation and influencing the overall evolution of their host galaxies. As matter falls towards a supermassive black hole, it releases vast amounts of energy, heating the surrounding gas and driving powerful outflows. These outflows, often observed as jets of particles traveling at nearly the speed of light, can interact with surrounding gas clouds, triggering star formation. In some cases, the energy released by accreting supermassive black holes can quench star formation altogether, creating red and dead galaxies. This delicate balance between the feeding of supermassive black holes and the evolution of their host galaxies highlights the complex and interconnected nature of the cosmos. In the cold, unforgiving vacuum of space, black holes stand as silent sentinels, their presence marked not by light but by its absence. These enigmatic objects, born from the death throes of massive stars, are regions where gravity's dominion is absolute. At the heart of every black hole lies a singularity, a point of infinite density and zero volume. Yet surrounding this singularity is a boundary, a point of no return known as the event horizon. Imagine for a moment that you are an intrepid space traveler, embarking on a perilous journey to the edge of a black hole. As you approach this cosmic monster, you would notice nothing particularly unusual at first. The stars would still twinkle in the distance, their light seemingly unaffected by the black hole's presence. Finally, you would reach the point of no return, the event horizon. This boundary, often depicted as a spherical surface surrounding the black hole, is not a physical barrier in the traditional sense. It is simply the point beyond which the black hole's gravity is so strong that escape becomes impossible, even for light itself. Once you cross the event horizon, your fate is sealed. No matter how powerful your engines, you would be drawn inexorably towards the singularity at the black hole's core. As you plunge deeper into the black hole, the relentless pull of gravity would begin to distort your spacecraft, stretching it out in a process known as spaghettification. This bizarre effect arises from the difference in gravitational pull across the length of your spacecraft. The event horizon, however, is more than just a point of no return. It is also a region where our understanding of space and time is pushed to its limits. Massive objects like stars and planets create depressions in the fabric of spacetime, much like a bowling ball placed on a trampoline. These depressions are what we perceive as gravity. Black holes, with their immense density and gravitational pull, create the most extreme distortions of spacetime imaginable. Near the event horizon, spacetime is so warped that the usual roles of space and time are reversed. Inside a black hole, the singularity doesn't lie in the future as it would in normal spacetime.
The ergosphere, a realm of paradox. For non-rotating black holes, the event horizon marks the point of no return. However, most black holes are thought to rotate, adding a further layer of complexity and intrigue. Rotating black holes possess an additional region of spacetime outside the event horizon known as the ergosphere. The ergosphere is a place where strange and counterintuitive phenomena can occur. Objects caught within the ergosphere are inevitably forced to rotate with the black hole. This effect, known as frame dragging, is a consequence of the black hole's immense angular momentum.
Hawking radiation black holes, not so black. For decades, black holes were thought to be inescapable cosmic sinks. However, in 1974, Stephen Hawking made a groundbreaking discovery that would forever change our understanding of these enigmatic objects. Hawking showed that black holes, contrary to popular belief, are not entirely black. Instead, they emit a faint thermal radiation, now known as Hawking radiation, due to quantum effects near the event horizon. According to quantum mechanics, empty space is filled with virtual particle-antiparticle pairs that constantly pop into existence and then annihilate each other. Hawking realized that if such a virtual particle pair were to be created near the event horizon of a black hole, one particle could fall into the black hole, while the other escaped to infinity. The escaping particle would carry away a small amount of energy from the black hole, effectively reducing its mass over time. The information paradox, a cosmic conundrum. Hawking's discovery of black hole evaporation raised a profound puzzle, the information paradox. According to quantum mechanics, information in the form of quantum states cannot be destroyed. This principle, known as unitarity, is fundamental to our understanding of the quantum world. However, the process of black hole evaporation seems to violate this principle. When a black hole forms, it swallows all the information about the matter that collapsed to create it. If the black hole evaporates completely via Hawking radiation, what happens to all the information that was trapped inside? The information paradox, far from being a mere theoretical curiosity, has profound implications for our understanding of the cosmos. It suggests that our current theories of gravity and quantum mechanics are incomplete and that a more fundamental theory, one that unifies these two pillars of modern physics, is needed to fully explain the nature of black holes and the universe itself. Physicists have proposed a number of possible solutions to the information paradox, each with its own set of intriguing implications. Some theories suggest that information is not truly lost inside a black hole, but is somehow encoded in subtle correlations within the outgoing Hawking radiation. Others propose that black holes do not evaporate completely, but leave behind remnants, tiny objects that preserve the information about the matter that fell into the black hole. The search for a solution to the information paradox has driven much of the progress in theoretical physics in recent decades. It has led to the development of string theory, a framework that attempts to unify all the fundamental forces of nature, including gravity, into a single coherent theory. It has also sparked new insights into the nature of quantum gravity, the elusive theory that would reconcile general relativity with quantum mechanics. For centuries, black holes remain shrouded in mystery, their existence inferred from indirect evidence, their true nature a subject of intense speculation. Astronomers, limited by the electromagnetic spectrum, could only observe the effects of black holes on their surroundings. The swirling accretion disks, the powerful jets of particles, the gravitational pull on nearby stars. But the black holes themselves, hidden behind their event horizons, remained elusive, their secrets locked away in the depths of spacetime. However, a new era of astronomy was dawning, one that promised to unveil the invisible and reveal the secrets of these cosmic enigmas. This revolution was not driven by light, but by gravity itself, by the subtle ripples in the fabric of spacetime that emanate from the most violent events in the universe, the collisions of black holes. These ripples, known as gravitational waves, were first predicted by Albert Einstein in 1916 as a consequence of his theory of general relativity. Einstein showed that massive objects, when accelerated, create disturbances in spacetime, much like a boat moving through water creates waves. These gravitational waves, however, are incredibly weak, far weaker than any other known force in the universe. Detecting them would require instruments of unprecedented sensitivity, instruments that could measure changes in distance smaller than the width of an atom. For decades, the search for gravitational waves remained a tantalizing dream, a quest pursued by a small but dedicated group of scientists who dared to challenge the technological limitations of their time. The challenge lay not only in the extreme faintness of gravitational waves but also in their unique nature. Unlike light waves, which are electromagnetic waves that travel through spacetime, gravitational waves are ripples in spacetime itself. Detecting them would be like listening to the universe breathe, sensing the subtle vibrations of the cosmic drum. In the 1970s, a team of physicists led by Rainer Weiss at MIT began developing a revolutionary new type of instrument designed specifically to detect gravitational waves. Their idea was deceptively simple, yet technologically daunting. Use lasers to measure the minute changes in distance between mirrors suspended kilometers apart. Any passing gravitational wave, they reasoned, would stretch and squeeze spacetime, causing the distance between the mirrors to fluctuate ever so slightly. This concept, known as laser interferometry, formed the basis for the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two identical detectors, one located in Hanford, Washington, and the other in Livingston, Louisiana, separated by 3,000 kilometers. Each detector consists of two 4-kilometer-long arms arranged in an L shape, with mirrors suspended at the ends of each arm. Laser beams are bounced back and forth between the mirrors, and their interference patterns are carefully monitored for any telltale signs of a passing gravitational wave. Listening to the cosmos. The construction of LIGO was a monumental undertaking, a testament to human ingenuity and the relentless pursuit of scientific knowledge. It took decades of research and development, countless hours of engineering and construction, and the unwavering dedication of hundreds of scientists and engineers to bring LIGO to fruition. Finally, in 2002, LIGO began its first science run, its sensitive detectors poised to listen to the whispers of gravity from the distant universe. For years, LIGO listened patiently, its detectors humming with anticipation, but the cosmos remained silent. No gravitational waves were detected, and some began to doubt whether these elusive ripples in spacetime would ever be found. However, the LIGO team persevered, constantly upgrading their instruments, improving their sensitivity, and refining their data analysis techniques. Their persistence would be rewarded. In 2015, after a major upgrade that significantly enhanced LIGO's sensitivity, the detectors finally captured what they had been searching for: the faint but unmistakable signature of a gravitational wave. The signal, a brief chirp lasting only a fraction of a second, arrived first at the Livingston detector, and then, 7 milliseconds later, at the Hanford detector, confirming that it originated from a distant cosmic source. Cosmic Symphony of Destruction. The source of the gravitational waves, astronomers determined, was a pair of black holes, each about 30 times the mass of our Sun, locked in a death spiral billions of light-years away. As the black holes orbited each other, their immense gravity warped spacetime, radiating energy away in the form of gravitational waves. This loss of energy caused the black holes to spiral closer and closer together, their orbital speed increasing until they finally collided in a cataclysmic merger, releasing more energy in that brief instant than all the stars in the observable universe combined. The gravitational waves from this cosmic collision, traveling at the speed of light, spread out through the universe like ripples from a stone dropped in a pond. After traveling for over 1 billion years, these faint echoes of a long-ago cataclysm reached Earth, where they were captured by LIGO's sensitive detectors, marking a pivotal moment in the history of astronomy. The detection of gravitational waves from merging black holes not only confirmed a key prediction of Einstein's theory of general relativity, but also provided the first direct evidence for the existence of these elusive objects. Furthermore, it opened up an entirely new way of observing the universe, one that did not rely on light but on the very fabric of spacetime itself. Capturing the shadow of infinity. The groundbreaking detection of gravitational waves by LIGO in 2015 heralded a new era of astronomy, one in which we could listen to the whispers of gravity from the most extreme events in the universe. But astronomers were not content with merely listening to the cosmos. They yearned to see the invisible, to capture an image of a black hole, the most enigmatic object in the universe. This dream, once thought to be impossible, became a reality thanks to the Event Horizon Telescope, EHT, a global network of radio telescopes linked together to create a virtual telescope the size of Earth. The EHT's target was Sagittarius A*, a supermassive black hole lurking at the center of our Milky Way galaxy, about 26,000 light-years from Earth. Observing Sagittarius A* is a daunting task. Despite its immense mass, equivalent to about 4 million suns, the black hole itself is incredibly small, about 44 million kilometers across, or roughly the size of Mercury's orbit around the Sun. Furthermore, it is shrouded by a thick cloud of gas and dust, obscuring it from view at visible wavelengths. To overcome these challenges, the Event Horizon Telescope observes Sagittarius A* at radio wavelengths which can penetrate the obscuring gas and dust. By combining data from multiple telescopes around the world, the EHT creates a virtual telescope with an angular resolution sharp enough to resolve the black hole's event horizon, the point of no return for light and matter. In April 2019, after years of planning, observation, and data analysis, the EHT team unveiled the first-ever image of a black hole, a stunning achievement that captivated the world and ushered in a new era of black hole astrophysics. The image, a testament to the power of human ingenuity and international collaboration, shows a bright ring of light surrounding a dark central region, the black hole's shadow. The bright ring arises from the superheated gas and dust orbiting the black hole at nearly the speed of light. As this material swirls around the black hole, it emits radio waves that are lensed and distorted by the black hole's intense gravity, creating the observed ring-like structure. The dark central region, the black hole's shadow, is a region of spacetime so warped by gravity that not even light can escape. Its size and shape are consistent with the predictions of Einstein's theory of general relativity, providing further confirmation of this groundbreaking theory in the most extreme gravitational environment yet observed. The EHT's image of Sagittarius A* is more than just a stunning visual. It provides a wealth of information about the black hole's properties, such as its mass, spin, and orientation. By studying the details of the bright ring and the dark shadow, astronomers can learn about the behavior of matter and light in the presence of extreme gravity, testing the limits of our current understanding of physics. The era of black hole astronomy has just begun. With new telescopes and instruments coming online, we are poised to unravel the mysteries of these enigmatic objects in unprecedented detail. From the echoes of gravitational waves to the shadows of event horizons, black holes continue to captivate our imaginations, reminding us of the vastness of the cosmos and the boundless capacity of human curiosity. From the earliest whispers of dark stars to the groundbreaking images captured by the Event Horizon Telescope, the story of black holes is a testament to the enduring power of human curiosity and our relentless pursuit of knowledge. For centuries, these enigmatic objects have captivated our imaginations, challenging our understanding of the cosmos and pushing the boundaries of theoretical physics. What began as a series of thought experiments, a contemplation of gravity's ultimate dominion, has blossomed into a vibrant field of research, fueled by technological advancements and the collective efforts of scientists around the world. The journey that led us to our current understanding of black holes has been marked by both moments of profound insight and periods of frustrating uncertainty. From John Michell's initial conception of dark stars to Albert Einstein's revolutionary theory of general relativity, which provided the theoretical framework for understanding black holes, each step forward has been a testament to the power of human ingenuity to unravel the secrets of the universe. The discovery of Cygnus X1, a binary star system harboring a stellar mass black hole, provided the first concrete evidence that these objects were not merely theoretical constructs but existed in the real universe. The subsequent development of X-ray astronomy opened up a new window into the cosmos, revealing the presence of supermassive black holes lurking at the hearts of galaxies, their immense gravitational pull shaping the evolution of these cosmic behemoths. Uncharted territories. Despite these remarkable advancements, our journey into the realm of black holes is far from over. In many ways, we have only just begun to scratch the surface of these enigmatic objects, our understanding limited by the current boundaries of our knowledge and the technological capabilities of our instruments. Yet, with each new discovery, each tantalizing glimpse into the depths of spacetime, new questions arise, beckoning us to venture further into the unknown. The detection of gravitational waves by LIGO and Virgo, a testament to the power of human ingenuity to measure the most subtle vibrations of the cosmos, has opened up an entirely new avenue for studying black holes. These ripples in spacetime, generated by the most violent events in the universe, carry with them encoded information about the objects that created them, their masses, spins, and even their compositions. As our ability to detect and analyze gravitational waves improves, we can expect a symphony of cosmic signals, revealing the hidden mergers of black holes and neutron stars throughout the universe. These observations will provide invaluable insights into the formation and evolution of these extreme objects, shedding light on the processes that govern the dynamics of the cosmos. Black holes, once thought to be isolated oddities, are now recognized as integral components of the cosmic tapestry, their influence extending far beyond their immediate surroundings. They play a pivotal role in the evolution of galaxies, regulating star formation, shaping the distribution of matter, and even influencing the large-scale structure of the universe. Supermassive black holes lurking at the centers of most galaxies are thought to have played a crucial role in the formation and evolution of their host galaxies. Their immense gravitational pull draws in surrounding gas and dust, fueling their growth and triggering bursts of star formation. The energy released during these accretion processes can heat up the surrounding gas to millions of degrees, driving powerful outflows that can influence star formation rates across entire galaxies. Furthermore, black holes are thought to play a role in the distribution of dark matter, the invisible substance that makes up the majority of the mass in the universe. The gravitational pull of black holes can act as seeds for dark matter halos, the vast invisible structures that envelop galaxies and influence their interactions with one another. Perhaps the most profound questions surrounding black holes lie at the intersection of general relativity and quantum mechanics, two of the most successful theories in physics, yet inherently incompatible with each other. General relativity describes the universe on the largest scales, the realm of stars, galaxies, and the fabric of spacetime itself. Quantum mechanics, on the other hand, governs the universe on the smallest scales, the realm of atoms, subatomic particles, and the bizarre rules that govern their behavior. The singularity at the heart of a black hole, a point of infinite density and zero volume, represents a breakdown of general relativity, a point where our current understanding of physics crumbles. It is here, at the boundary of the infinitely small, where quantum effects are thought to become dominant, potentially offering a glimpse into the quantum nature of gravity. The information paradox, the question of what happens to information that falls into a black hole, highlights the clash between these two fundamental theories. While general relativity suggests that information is lost forever inside a black hole, quantum mechanics dictates that information cannot be destroyed. The quest to understand black holes is ultimately a quest to understand the universe itself, its origins, its evolution, and its ultimate fate. These enigmatic objects, once relegated to the realm of science fiction, have emerged as cosmic laboratories, testing the limits of our knowledge and pushing us to develop new theories and technologies to probe the depths of the cosmos. The future of black hole research is bright, filled with the promise of new discoveries and the potential to revolutionize our understanding of the universe. New telescopes and instruments, both on Earth and in space, will provide us with unprecedented views of black holes, revealing their secrets in greater detail than ever before. We can expect to witness the birth of black holes in real time, observing the death throes of massive stars as they collapse into these cosmic abysses. We will map the distribution of black holes throughout the universe, tracing their evolution over cosmic time and unraveling their role in the formation of galaxies and the large-scale structure of the cosmos. The story of black holes is a story of exploration, discovery, and the boundless capacity of the human spirit to unravel the mysteries of the universe. It is a story that transcends generations, inspiring awe and wonder in all who dare to gaze up at the night sky and contemplate the profound implications of these cosmic enigmas. As we continue our journey into the realm of black holes, we embark on a voyage of discovery, not only of the cosmos but also of ourselves, our place in the universe, and the limits of our understanding. It is a journey filled with challenges, setbacks, and moments of profound revelation. A journey that reminds us that the universe is far stranger, far more wondrous, and far more awe-inspiring than we could ever have imagined. The quest to understand black holes is an invitation to explore, to question, and to marvel at the intricate workings of the universe. It is a reminder that we live in a universe of infinite possibilities, a universe where the boundaries of knowledge are constantly expanding, and where the greatest discoveries may yet lie ahead.